The birth of optical fibre communication. 50 years ago, the optical fibre revolution began with a small team at a British research laboratory. This is their story. The presentation that follows was given at a special symposium to celebrate the 50th anniversary of low-loss optical fibres in 2016. It was part of the Frontiers in Optics Conference held in Rochester, USA, which was also the 100th annual meeting of the Optical Society of America. In 1966, Sir Charles Kao and George Hockham published their historic paper titled Dielectric Fibre Surface Waveguides for Optical Frequencies. The paper predicted that optical fibre communication would be possible if various problems could be solved. It was also a memorable time for me personally, the beginning of my own adventure with light. I had just graduated from Manchester University in England, where my colleague and I had designed and built a free space optical communications link as our final year project. The experience of thick city fogs in that coal-burning era dramatically revealed the limitations of trying to communicate optically through the air. After graduating, I spent the summer exploring North America on the Greyhound buses. $99 for 99 days. It was an incredibly good deal, as the price was completely independent of the distance travelled. In contrast, calling long distance on the phone was much more costly. On my travels, I saw the Bell Labs picture phone. It looked cool, but cost $27 for a 3-minute call from New York to Chicago. That's more than 1,000 times more per minute than my Greyhound bus deal. On my return to England, I was fortunate to begin work at Standard Telecommunication Laboratories, or STL as we know it. It was just a few months after Charles Kao and George Hockham had published their historic paper. To put optical fibre into perspective, we must go back to the end of the Second World War, a time when we had a copper wire-based telephone system. Our experience of television in our homes soon led to the idea that we would all want personal video phones, and that this would soon demand much more electronic connectivity. Multiplexing now enabled many channels to be combined into fewer cables, and digital transmission was being developed. Each cable in this multi-coax cable could carry 120 megabit per second data. That's 2,000 simultaneous phone calls. But the cable was bulky and difficult to pull into ducts under the street. The copper material used was expensive and still is, and repeaters were required every 2 kilometers to regenerate the signal. The war had driven the development of microwave technology for radar, but when peace came, microwave experts applied their skills to communications and developed point-to-point microwave links. The higher carrier frequency offered much greater information capacity than previously available. However, the search was on for a technology to replace the copper cables of the telephone network with something of much higher capacity. A natural step was to investigate the use of guided microwave signals in a long-haul waveguide structure. Bell Labs established a large program, as did the British Post Office and my own lab's STL. When optical fibre struggled to be born, this was its major competitor, what we might have implemented instead if fibre had not emerged the winner. It was a 4-inch diameter fibreglass tube, the inside of which was lined with a helical copper wire. The design suppressed unwanted modes of propagation and permitted some slight bending. The attenuation was remarkably low for the information rate, just 3 dB per kilometre. This was the vision of the future in 1960. However, there were major problems. Bends had to be very large radius to avoid mode conversion, and manufacturing was slow and consumed costly materials. This was the manufacturing process. First, insulated copper wire was wound onto a solid former. Lossy graphite fibre was then wound on top, followed by a layer of fibreglass and the whole assembly soaked in resin, and it was then transferred to an oven and cured for several hours. Finally, the former was pulled out, all this for a short length of microwave waveguide. Now contrast this with how optical fibres are made. Many kilometres of thin fibre are drawn down from a short and much thicker preform. For our company, 1959 was the high point in the long-haul microwave waveguide story. This was our test range, with 4 lengths of waveguide. The inner pair you see here were of the construction I've just described. This was their idea of a flexible structure, much less flexible than everything that had gone before. The minimum allowable bend radius was several hundred feet. Not long after this photo was taken, the company stopped all further work on the project. Bell Lab's own extensive program continued until the mid-70s, delaying their involvement in the optical fibre revolution. Later, when fibre began to show promise, we took this photo to emphasize the point about comparative flexibility. It was even suggested that these hollow tubes would make ideal ducts for installing the optical fibre cables. These failed microwave waveguide programs paved the way for optical fibre, in that they planted the idea of a single waveguide carrying a high information capacity. And they subsequently provided many waveguide experts to work on optical waveguides. And then things changed. Light-emitting diodes and lasers were invented. This triggered research into optical communications. Now we had light sources with very high brightness and high spectral purity. With a carrier frequency 4 orders of magnitude higher, the information carrying potential of an optical system was vast. In 1959, when the standard telecommunications laboratories were moved to a new facility in Harlow, a small team was established to explore possible techniques for guided optical communication. The team was initially led by Alec Reeves, famous for inventing pulse code modulation, the basic idea of error-free regeneration of digital signals. Initially, the team focused on guiding the energy in air, for it was assumed that dielectric materials such as glass could never be made sufficiently transparent. The optical pipeline was one waveguiding system which was tried. Although the internal surface was silvered, the theory predicted low loss at very shallow angles. Here is the 1-inch diameter tube running alongside the building. Unfortunately, experiments revealed the loss to be far higher than predicted. Instead of 2.5 dB per mile, they measured 200 dB per mile. Bends would have been a problem too, as even the theory demanded bends of more than a quarter-mile radius. But remember, it was still being compared with a very inflexible microwave waveguide. It was very temperature sensitive and only worked briefly twice a day, just as the ambient temperature stabilized. So in 1962, that was the end of the optical pipeline. The labs also experimented with a confocal lens system. This used a sequence of lenses spaced 100 meters apart each refocusing the beam. But once again, alignment problems and temperature sensitivity killed it. Although Bell Labs had invested heavily in their ongoing microwave waveguide system, they too explored optical waveguides at this time, with optical pipes and a novel confocal system using gas lenses in which a thermal gradient created the lensing effect. Meanwhile, STL began to investigate dielectric guides, but ones in which the majority of the power propagated in air. The thin film planar waveguide used a polycarbonate film only 1/10 of a micron thick, but the confinement was weak and light escaped at bends. They tried using equally thin glass fibres, but they proved impossible to support and to handle. They were invisible, and being so light they just floated away. Charles Kao was born in Shanghai in 1933 and moved to London to take his bachelor's degree. He completed a PhD on mode conversion in long-haul microwave waveguides and then joined the parent company, Standard Telephone and Cables, where he met his wife Gwen, a software programmer. In 1960 they moved to the new STL labs in Harlow, with Charles initially working in the microwave lab before transferring to the Optical Communications program in 1963. He immediately set to work exploring all the options for a low-loss optical guiding mechanism, while George Hockham joined him a little later. Charles was soon left in charge of the whole optical communications project. It now seemed clear to Charles that attempts to guide light through the air were doomed to failure, so he began to explore the idea of guiding the light completely inside a strand of glass, despite knowing that the purest glass available at the time was far too lossy to be of practical use. It was well known that a solid glass fibre would guide light, but only if the surface was not touched. In 1954, Van Heel had come up with the answer: to surround the guided core with a thin protective transparent cladding of lower index, so the light was reflected at the core cladding boundary. Curtis and others subsequently built upon this idea by using a glass cladding. Here at last was a truly practical light guide which found many applications. The best fibres at the time had a loss of around 1 decibel per metre, or 1,000 decibels per kilometre, so were unsuitable for communicating over distance. These fibres were highly multimoded and used a thin cladding with a large core to maximise the captured light. In 1961, Elias Schnitzer published a theoretical description of a single-mode dielectric guide. But as the loss in glasses was so high at that time, no one envisaged its use in transmission systems. While the pattern of light emerging from a multimode fibre is influenced by the launch conditions, in the single-mode fibre only intensity information is communicated to the far end. Charles became increasingly convinced that a single-mode optical waveguide in glass might be the answer. Despite objections, even ones from within the company, Charles persisted enthusiastically with the idea. There were many potential reasons to fail, not just absorption loss, and Charles and George began to address each in turn through a combination of theoretical analysis and experiments. They experimented with early fibre samples. Here is the world's first single-mode communications fibre, still in its original display box. These early fibre samples showed little promise and only transmitted light over a few meters. If the vision was to be realized, they had to investigate whether there were any fundamental mechanisms that could not be overcome, such as losses due to absorption, scattering and bends. Could the fibre be made with sufficient geometrical accuracy? Could it handle sufficient power? They addressed all these concerns, culminating in their historic paper. They predicted the degree of purity required. Note that the lowest absorption loss they measured at that time was in the visible. They estimated the scattering loss could be just a few dBs at 1 micron wavelength. George Hockham modelled the fibre behaviour theoretically, and he also simulated the effect of possible fibre diameter variations through experiments with fin rod microwave waveguides. The periodic variation in fin depth simulated fibre diameter variations over different scale lengths. His experiments with bends in microwave guides, when scaled to optical frequencies, showed that tight bends would be possible in fibre. They explored the light patterns emerging from the end of short fibre samples, looking for true single-mode operation. These were the paper's conclusions. An information capacity in excess of 1 GHz. It's completely flexible and requires a mechanical tolerance of 10%, which can easily be met in practice. Advantages in basic material cost. The realization of a successful fibre waveguide depends on the availability of suitable low-loss dielectric material. The crucial material problem appears difficult but not impossible. The required loss figure of 20 dBs per kilometre is much higher than the lower limit of loss figure imposed by fundamental mechanisms. They described a flexible single-mode fibre made of glass with a core cladding index difference of 1%, which had the potential to provide long-distance communication at very high information rates, provided the loss could be reduced to 20 dBs per kilometre. The paper demonstrated that the prohibitively high loss of early samples was not fundamental and could be reduced sufficiently to make optical fibre a far more practical solution than other competing approaches. In January 1966, Charles Kao described progress at an IEEE conference in London. This press release from that time includes a prophetic quote. "It should be noted that when these methods are perfected, it will be possible to transmit very large quantities of information, telephone, television, data, etc., between, say, the Americas and Europe along a single undersea cable." Most believed it to be an impossible dream. I do remember that many greeted the idea with ridicule and hostility. Even I thought the undersea bit was a bit crazy. Charles knew the idea would get nowhere if the STL team in Harlow pursued the idea alone. So instead of patenting the idea, he travelled to research labs in the US, Japan, France and Germany, spreading the idea. In the UK, the British Post Office and the Ministry of Defence soon began to support the initiative. Fused silica had shown promise, so Charles acquired better samples from Corning and shot glass for evaluation. One meticulous member of the team had measured the loss of a very pure bulk sample of fused silica. He returned excitedly claiming the loss was 0 plus or minus 4 dB per kilometre. Everyone laughed. Even plus 4 dB per kilometre seemed unbelievably small, and of course minus 4 dB would have meant optical gain. So for years we quoted the figure of 4 dB per kilometre as the absolute ultimate limit, never realizing that a figure much closer to 0 would be achieved in time. It proved extremely difficult to measure the bulk loss over the short sample lengths available. Greater accuracy was achieved by measuring the differential attenuation between two identical samples but of different lengths. Despite all efforts to purify the glasses, fibre losses stayed stubbornly high, around 200 dB per kilometre. That was 10 times higher than the paper had predicted would be necessary to make fibre systems viable. It was very difficult to work with tiny core dimensions of single-mode fibre. Coupling losses were high. There were as yet no suitable light sources. LEDs weren't bright enough, and early gallium arsenide lasers had unstable transverse modes. So everyone started to make fibres with large cores, which made it much easier to measure the dominant loss mechanisms. As high loss meant we couldn't go far, dispersion was not a problem initially. When losses reduced and distances increased, greater index fibres were developed, providing lower dispersion. So for several years, single-mode fibre was ignored, and multimode fibre became the hot topic. So far, the glasses used had been made from natural materials such as sand from a nice white beach, so contained contaminants and imperfections. Corning Glass Company developed a new process creating synthetic glass from oxidized chemicals. With this exciting development, fibre systems suddenly became viable. When I arrived at the labs in 1966, I was tasked with converting this existing free space optical link to use optical fibre. I assembled a 20-metre fibre bundle using shot optical fibre. Note that the total fibre loss was 24 dBs, similar to that of many of today's fibre transmission links, but we could only go 20 metres. When white light was coupled into the bundle, it emerged green. When Charles Kao was seconded to Hong Kong University, Murray Ramsey headed the optical communications team. Here is Murray, in unusually smart attire, pointing out the finer points of fibre transmission to an important person. In 1973, with Corning's breakthrough in fibre loss, it was time to boost the program size. Harold Janine was the godfather of ITT, our parent company. He demanded to see a demo before he would sign off the significantly increased research budget, so I put this together for him. We could now go 2 kilometres and only needed a single fibre. An enterprising salesman from our parent company seized the opportunity to sell one of these to a paying customer to replace a coaxial cable-based communication link after lightning had knocked it out. In hindsight, this became the world's first commercial fibre transmission system. So meanwhile, what had happened to the competing technology of the microwave waveguide? In 1975, Bell Labs were still pursuing it, but by 1977 they admitted defeat. In a special issue of the Bell System Technical Journal, they described in great detail their 14-kilometre long millimetre waveguide field evaluation test. While they argued that its cost per carrying capacity would be low, there remained major problems, including its high cost and its inflexibility. In that very same year, we had just installed a 140 megabit per second fibre system between 2 towns in England and demonstrated its use as part of the UK telephone network. The 3-kilometre range between regenerators was crucial because the existing coaxial cable system required regenerators every 2 kilometres. We had to design and make almost every part of this optical system ourselves, being a completely new technology. Soon, fibre loss had been sufficiently reduced that one could directly connect fibre between all the UK telephone exchanges without any intermediate regenerators, thus eliminating the need for these footway boxes. When you try to implement a real practical system, there can be some nasty surprises. When this complete system was first tested in the lab, to our horror it didn't work. We had discovered a fundamental problem when using multimode fibre with coherent lasers: modal noise. Multipath interference in the fibre produced speckle, and mode conversion at imperfect joints in the fibre path created noise. Our quick solution was to decohere the laser's emission, but the experience taught us much, and it was the start of a trend back towards single-mode fibre. The other problem with graded index multimode fibre in the field was the unpredictable bandwidth. When joining sections of fibres from different manufacturers, it proved impossible to accurately predict the overall mode dispersion. So in the 1980s, we saw a return to the single-mode fibre which Charles Kao originally envisaged. With improved geometrical precision, single-mode fibres could now be joined with little excess loss. We were now planning transoceanic systems, and these demanded fibre with very low dispersion and loss. And, to everyone's delight, single-mode fibre proved cheaper to manufacture. So Charles's single-mode vision, expressed in that very first press release, finally became a reality. In 2009, Charles Kao was awarded the Nobel Prize in Physics. Sadly, Charles' own light is now dimming, for he has been suffering from Alzheimer's disease since 2004. He is now cared for by his remarkable wife Gwen in their home in Hong Kong. She too played a part in this story. For half a century ago, she wrote several of the Fortran computer programs used by Charles and George to simulate the optical waveguide behavior. Gwen now runs a charity in Charles's name to raise public awareness of Alzheimer's disease. So now I'd like to reflect on fibre's significance. What if we had no optical fibre communications? The alternative was the long-haul microwave waveguide, which was very expensive to make and to install. Its inflexibility would have confined its use to major routes. It's not practical to make thousands of miles of hollow gas-filled pipe withstand the 800 atmospheres of pressure 5 miles deep in the ocean. And by today's standards, it had a very low information capacity. Today's World Wide Web is possible because communication is now incredibly cheap and is independent of distance, and because fibre provides extraordinarily high information capacity. Furthermore, oceans are no impediment. Perhaps if fibre had never happened, we would be living in a more parochial world today, confined to our islands of information. You may remember that I began with a 50-year-old comparison of the high cost of long-distance communication compared with travelling by Greyhound bus. There are indeed similarities between the impact of the invention of the wheel and the invention of optical fibre. Transporting material or information takes energy. The wheel reduced the energy needed to move things and increase the speed of movement. Optical fibre has done the same for information. In conclusion, Charles Kao anticipated the low loss of silica-based glasses, but fibre communications only became a commercial reality as a result of the subsequent pioneering work developing low-loss glasses at Corning and elsewhere. I have only mentioned a few of the key players in this story, but must acknowledge the thousands of brilliant scientists, engineers and chemists who found practical solutions to the many problems encountered along the way. You can see the original paper and plenty more historical information at this website. For a more complete story of these early years, I highly recommend reading City of Light by Jeff Hecht and the biography A Time and a Tide by Charles and Gwen Cahill. Finally, I'd like to thank the Optical Society of America for inviting me to come and give this talk. Back home in the UK, we Brits have hardly noticed the significance of this key anniversary. I leave you with this brief 8mm film discovered in a basement a few years ago. It shows Charles experimenting with optical fibre in the lab.